Good day, everyone. Today, we turn our attention to the foundational pillars of classical mechanics, the very principles that govern how objects move and interact in our everyday world, Sir Isaac Newton's 3 laws of motion. These laws, elegantly simple yet profoundly powerful, provide us with a framework for understanding everything from the flight of a thrown ball to the orbit of a distant planet. Let us calmly explore each one. Newton's first law, the law of inertia. Our journey begins with Newton's first law, often referred to as the law of inertia. This law states that an object at rest will remain at rest, and an object in motion will remain in motion with the same speed and in the same direction, unless acted upon by an unbalanced external force. Essentially, objects tend to resist changes in their state of motion. Consider these examples. A book on a table. Imagine a book resting peacefully on a table. It will stay there indefinitely, remaining at rest, unless you apply a force to pick it up, or perhaps an earthquake shakes the table. Its natural tendency is to maintain its state of rest. A passenger in a braking car. When you're riding in a car that suddenly applies its brakes, your body tends to continue moving forward, even though the car is slowing down. This feeling of being thrown forward is a direct manifestation of your body's inertia, its resistance to the change in motion. The seatbelt or dashboard eventually provides the unbalanced force to bring you to a stop. Newton's second law, the law of acceleration. Next, we encounter Newton's second law, which quantifies the relationship between force, mass, and acceleration. This law asserts that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. In simpler terms, a larger force produces a larger acceleration, and a larger mass requires a larger force to achieve the same acceleration. This is often summarized by the famous equation, F is equals to ma, where F is net force, m is mass, and a is acceleration. Let's look at some illustrations. Pushing a shopping cart. Imagine you're in a supermarket. If you push an empty shopping cart with a certain force, it accelerates readily. However, if you apply the exact same force to a cart loaded full of groceries, it will accelerate much more slowly. The greater mass of the full cart means it resists acceleration more effectively. Kicking a soccer ball. When a soccer player kicks a ball, the harder they kick, applying more force, the greater the acceleration of the ball, and thus the faster it moves. If they apply the same force to a bowling ball, it would accelerate much less due to its significantly greater mass. Let's try using the equation. If a 20 kg box is pushed forward and moved at a rate of 3 meters per second squared, how much force was applied to the box? We are using the equation F is equals to ma. In this problem, the missing value is the force. We can use this triangle to make it easy. Remember the units, mass is in kilograms, acceleration is in meters per second squared, and force is in newtons. Using the scenario in triangle, F is missing. So, F is equals to 20 kilograms times 3 meters per second squared. The answer is 60 newtons. Always use the triangle to make the second law easier. Newton's third law, the law of action-reaction. Finally, we arrive at Newton's third law, a principle that highlights the interactive nature of forces. This law states that for every action, there is an equal and opposite reaction. It means that forces always occur in pairs. When one object exerts a force on a second object, the second object simultaneously exerts an equal and opposite force on the first. Consider these scenarios. Walking. When you walk, your foot pushes backward against the ground, the action. In response, the ground pushes forward on your foot with an equal and opposite force, the reaction, propelling you forward. Without this reaction force from the ground, you wouldn't be able to move. A rocket launching. A rocket expels hot gases downwards at tremendous speed, the action. According to Newton's third law, these expelled gases exert an equal and opposite upward force on the rocket, the reaction, thrusting the rocket into space. This is why rockets can work even in the vacuum of space, where there's no air to push against. In conclusion, Newton's 3 laws of motion provide a powerful and consistent framework for understanding the mechanics of our universe. From the simple resting of an object to the complex dynamics of rocket propulsion, these laws demonstrate the elegant order that governs the physical world around us. They are a testament to the profound insights of Sir Isaac Newton and continue to be fundamental to physics and engineering today.